Down there, life continues. The traffic is awful, stocks go on trading, and Star Trek is still showing.
Good day, grade 9s. Welcome to today's lesson for Natural Sciences. This is our very last lesson for term 3. So the knowledge area is still energy and change. And please remember that this section contributes 80 marks towards your final examination. So pay attention and take advantage of the marks because they're relatively easy to get. The topic for today's lesson is series and parallel circuits, and the subtopic is parallel circuits. I'm sure by now you know my name. My name is Kwanele Dlamini, and this lesson is proudly brought to you by the Gauteng Department of Education. So without any waste of time, let us begin. So what's the point of this lesson? What are we trying to achieve? We are trying to ensure that by the end of this lesson, you should be able to explain that the voltage is the same across each resistor that is connected in a parallel circuit. You should be able to explain that the voltage is the same across each resistor that is connected in a parallel circuit. You should also be able to explain that the total current through the battery is equal to the sum of the currents through each of the resistors connected in parallel. You should also be able to state that the total current in the circuit increases as more resistors are added in parallel. You should be able to state that the total current in the circuit increases as more resistors are added in parallel. For more information on this, you can refer to the grade 9 CAPS document on page 73. Let us continue. So now let's take a step back and revisit some of the concepts that we've learned in previous grades because they lay a foundation for today's lesson. We are going to begin with grade 5 and 6. In grade 5 and 6, we learned about electric cells. But what are electric cells? You can think of an electric cell as a system in which certain chemical reactions can cause the flow of what? Electricity. It's a system in which certain chemical reactions can cause the flow of electricity through an external circuit. But in short, cells are known as the energy source in an electric circuit. They provide energy for electrons to move in a circuit. Right, so these are the common cells that we normally use when we connect our circuits, either in series or parallel. These are called AA 1.5 volt cells. Okay, we can connect these ones in series or we can connect them in parallel. It's very uncommon to have a circuit that connects these ones in parallel, but we can connect them in parallel. So when they are connected in parallel, the voltage is going to be the same as the voltage given by one cell. But when they are connected in series, we add each individual voltage to give us the total voltage. Okay. Then in grade 6 again, we learned about mains electricity. But what is mains electricity? Mains electricity is the electricity that we are using at home, right? So we normally use this device. This is called a DB board, right? We use this device to control. It's a control panel for the electricity usage at home. If maybe we need to change something or fix something that is broken in our circuit, we normally trip a switch in this DB board, which is connected to that line so that we don't get shocked when we try to fix whatever the problem is. And then if there is a problem within the circuit, this thing will automatically trip a switch that transmits current to that section of the circuit so that we don't end up having an explosion in the house. So this is a very important control panel for electricity at home. Each household should have at least one of these, okay, for safety purposes. Then in grade 7, we learned about the national electricity or the supply systems. But what is the national electricity and what are the supply systems? The national electricity is the overall process where electricity is generated from the power station where coal delivered from a mine is burnt to raise energy to heat up water to form steam, superheated steam. Then that steam provides energy for a turbine. The turbine then uses the energy from the steam, which is thermal energy or heat energy, to drive a generator. Then the generator will generate electricity, and the electricity is sent to a transformer. A transformer is a device that is used to either increase or reduce the voltage of electricity. So the transformer that the generator sends the electricity to is called a step-up transformer, where the voltage is increased to compensate for losses that are going to occur when the electricity is being transmitted over long distances using power lines which are supported by pylons. Okay? To compensate for the power losses, the electricity or the voltage is increased, and then the power lines transmit the electricity to a step-down transformer or substations where the electricity or voltage is reduced to a safe level for delivery to our households, businesses, and industrial areas. Okay, so that is the whole supply system from the source, which is the power station, all the way to the end user, which is the consumer. Okay, and this is what it looks like. You have coal coming from a mine, delivered into the power station. The power station has processes that I've explained already, where they convert energy from the coal into electricity, and then it's delivered through these transmission lines, then to a substation, and then boom, to the end user. Okay? Then in grade 8, we learned about energy transfer in electrical systems. But what are these energy transfers? When energy is being transferred, remember that we have the law of conservation of energy, which says energy cannot be created nor destroyed. It can only be transferred from one form to another. So energy transfers is when we use a certain type of energy and we convert it into another form of energy. Okay, so what energy changes can you think of that occur in electrical systems? I'm very interested in your ideas. But anyway, the very first energy transfer that we can think of occurs at the source, which is the power station. When we burn coal, we are generating what? Thermal energy, which is heat energy. Then that thermal energy is transferred into steam. It's still thermal energy. But then when it reaches the turbine uses it and converts it to mechanical energy, which is then used to power the generator. So here we have what? Heat or thermal energy converted to what? To mechanical. Because the turbine has blades that turn. That's kinetic energy there. That's thermal energy. So the steam comes to these turbines. This is one turbine, another turbine, another turbine, another turbine, and they turn so that they do work, which powers what? The generator. And then the generator converts mechanical energy into what? Electrical. Okay, so we have already 3 energy changes from thermal to mechanical, then electrical. Okay, hope you understand that so far. And then there are also other energy transfers that occurs even within the conducting wires or the power lines. Remember in our resistance lesson, we talked about how electrons encounter resistance in the conductor and they lose some of their kinetic energy in the form of heat. So there's heat losses here. So some of the energy is lost as heat. It's converted from electrical into heat. Okay? Right. Then when it reaches the end user, when you plug, let's say a stove at home, right, in the socket plug, you are going to convert what? Electrical energy into what type of energy? Any ideas? Yes, that is correct. It's going to be transferred into heat energy if you are using a stove, right? So the heat energy is going to be delivered by the coil, right? This coil here is going to encounter resistance. Okay, it has resistance. So while the electrons are trying to flow through it, they will bump into the molecules of this coil and they will lose some of their kinetic energy in the form of what? Of heat. And hence, this coil heats up. When this coil heats up, it's going to transfer that heat energy into the port. And then the port is going to transfer that heat energy into what? The water. And then the water would start to boil. So what energy transfer happened here? It's electrical from this. This is electrical. And we transferred it into what? Into heat. This is the useful energy transfer, the energy that we are using, right? But then there's also another form of energy that is transferred, okay? This electrical is transferred into two forms of energy. One is heat, which is our useful energy, and then there's light. As you can see, this element is glowing. So there's light energy as well. But unfortunately, we can't use that light energy. So it's what? It's a lost energy or wasted energy, okay? So here we're converting what? Electrical into heat and light energy. Another example which is relevant for our lesson is the circuit, right? In a circuit, we use a cell or battery, and there's chemical reactions that are occurring within the cell. The cell on its own has chemical potential energy. As soon as we connect wires to it and attach it to a resistor, we are generating electrical energy. So we are converting what? Chemical potential energy into electrical energy. Then that electrical energy is supplied to a bulb or a resistor. That bulb is going to glow, and when it glows, it has what? Radiant or light energy, right? So we converted what? Electrical into light. But then when you touch the surface of that bulb, you're going to feel that it gets warm. So there's also what? Thermal or heat energy. So the energy conversions here are from chemical potential, let's write that, chemical potential energy into electrical energy, then light or radiant, and thermal and heat. Okay, so these are different forms of energy conversions that occur within electrical systems. They are not limited to this. These are just a few examples that I can give. Let us continue. Now let's do a baseline assessment, which is nothing but a revision of concepts that we either already know or we are about to discuss further. So I have a couple of questions for you that you can do to test how much you understand about the concepts. The very first question is an ammeter connected in series or parallel, and why? Question 2, what happens to the current in a parallel circuit when we add more resistors? Question 3, what is the unit of measurement for current? And lastly, why does current not flow when we connect a voltmeter in series? You have 4 minutes to work through these questions and feel free to discuss with your friend. I'm very interested in your answers. Your time begins now. Alright learners, welcome back. I hope you were able to work through those easy questions. Let's quickly discuss the answers together. The very first question was, is an ammeter connected in series or parallel and why? Okay, an ammeter is always connected in series regardless of what type of a circuit you have. If you want to measure the current passing through a certain component in your circuit, you have to connect your ammeter in series to that component. The reason is ammeters have a negligible resistance, so they don't affect the flow of current. Okay, they have a very low resistance and they permit the flow of current. Question 2, what happens to the current in a parallel circuit when we add more resistors? Anyone? Yes, that is correct. When we add more resistors in a parallel circuit, the current is going to increase. Why? That is because we are using less energy from the battery to overcome the resistance. In a parallel circuit, when you add more resistors, the overall resistance or the equivalent resistance of that parallel circuit will decrease. Okay? But in a series, the resistance increases and hence the current strength will decrease. Okay, don't confuse the two. Question 3, what is the unit of measurement for current? I'm sure everyone should be able to get this one correct. What is the answer? Yes. The unit of measurement for current is the ampere. We use a capital letter A for amperes, okay? So why does current not flow when we connect a voltmeter in series? Why? Yes, that is correct. The reason is because a voltmeter has a very high resistance and hence it will not allow current to flow. Okay, it will prevent the flow of current. Okay, let's move on. I hope you were able to get these questions correctly. If you did, well, congratulations, well done. Before we continue, I would like to remind you that if you have a question or you need clarity on anything that we've discussed so far, please don't be shy to forward it to our WhatsApp line, which is 064 748 8913. That's 064 748 8913. Send your question through and we will kindly assist you. Let's move on. Now let's define a couple of terms that we are going to encounter in the lesson so that we don't need to consult Google or the dictionary to find meaning, okay? The first term is current. What is current? Current can be defined as the flow of electricity or charge through a conductor. Right. Current is generated by the flow of what? Of electrons in a conductor, right? It's very easy to confuse current with electrons. So let's try and distinguish the two so that we completely understand how they differ from each other. Electrons are flowing from the negative terminal of the cell or battery into the external circuit and back to the positive terminal of the battery or cell. Current, on the other hand, flows in the opposite direction. Current is generated by the flow of electrons, but it flows from the positive terminal of the battery or cell through the external circuit and then back to the negative terminal of the battery or cell. So that's the two differences between current and electrons. Okay, the flow of electrons give rise to the generation of current, but they flow in opposite directions. Okay, let's move on. The ohm. What is the ohm? The ohm is the unit of measurement for resistance, right? We use the Greek symbol omega to represent the ohm, which is the unit of measurement for what? For resistance. The next term is an ammeter. What is an ammeter? An ammeter is an instrument that we use to measure current. And the units are amperes, right? With capital letter A. So current is measured in amperes, Resistance is measured in what? Ohms. Okay. Let's continue. Now let's define a parallel circuit. What is a parallel circuit? It is an electric circuit that has more than one pathway for current to flow. Okay. An electrical circuit that has more than one pathway for current to flow. So the difference between this one and a series circuit only has one pathway. Okay, there's one pathway from the battery to the external circuit and then back to the battery. But with a parallel circuit, there's different pathways from the battery to different branches of the circuit and then back to the other terminal of the battery. That is a parallel circuit. Right, so now I have a question before we begin our lesson. What happens to the voltage across cells as more cells are added in parallel? I'm very interested in your answers. What do you think? You can discuss with your friend. What do you think? What happens to the voltage across cells as more cells are added in parallel? Okay. Well, if you paid attention when I was talking about electric cells, you would remember that the voltage of parallel cells is the same as the voltage of one of those cells. Okay, so if the cells each contribute 1.5 volts, when they are connected in parallel, their voltage is going to be the same as the voltage of one cell. Okay, I hope you remember that. Now let's talk about connecting resistors in parallel. Okay, we know that resistors are conductors that oppose the flow of current through them. Okay, they make it difficult for current to flow through themselves. So resistors can be connected in series, as you saw in our previous lesson, but they can also be connected in parallel. What does that mean? That means they can have multiple pathways for current to flow through them. Okay, and the voltage in a parallel circuit is the same across each resistor that is connected in parallel. So the voltage does not change provided the resistors are connected in parallel. So the voltage across the first resistor will be equal to the voltage across the second resistor provided they are parallel to each other, and it will be equal to any other number of resistors. That's what Vn means. And it will be equal to the voltage coming from the battery. That's what V battery means. Okay, so to demonstrate this, I have this illustration below. You have a battery that is providing 6 volts of voltage. That 6 volt will remain the same provided that the resistors are connected in parallel. The first resistor receives 6 volts and the second resistor receives the same 6 volts. So in a parallel circuit, the voltage remains constant. The only thing that changes is the current. Okay, as you can see, imagine this being current and it splits at this point, and then part of it goes there, that's I1, and then part of it goes there, that will be I2. Okay, the total current through the battery is equal to the sum of the currents passing through each of the resistors connected in parallel. We said the current has multiple pathways, so the total current that was delivered by the battery is split amongst the resistors. So to find the total current coming from the battery, we will have to add, and the sum of the currents that are passing through each of the branches will be equal to the current coming from the battery. Right, so the total current from the battery is equal to the current flowing through the first resistor in the parallel circuit plus the second current passing through the second resistor in the parallel circuit, and then if you have 3 of them, you're going to add the current flowing through the third one. So adding these 3 should give you the total current coming from the battery. Right, so to illustrate this, we have the battery. Remember, current flows from the positive terminal but electrons flow from the negative terminal. Okay, so electrons are flowing in that direction, current is flowing in that direction. So the total current that is measured here by this ammeter is 18 amps. And if these resistors are equal in resistance, they will split that current equally. But if they are not, the resistor with the least amount of resistance will take more current. And then the resistor with the highest resistance will take less current. So, assuming these resistors are equal in resistance, each of them is going to split 18 equally, right? 18 amps is the total current, and we divide it by 3 to split it equally amongst the 3 resistors. So the current is splitting here, that's the first point, and then it goes there and it splits again, and then it goes there and it splits again. So each resistor takes 6 amps, 6 amps, 6 amps. Why? Because they are equal, right? So 18 divided by 3 gives you 6. Okay? Let us continue. I hope that is clear. So this is another illustration showing how current splits. You have your voltage, and remember, current is always flowing from the positive terminal of the battery. So the battery provides voltage, and from the positive terminal we have our current flowing in that direction. This arrow represents current. This is your total current, I, and then it gets to this point where it splits. Part of it goes in that direction, part of it goes in that direction. The part that goes here is called I1, and then the part that goes in the other direction is I2, flows through resistor 2, right? They split the current. If they have equal resistance, they will split it equally. But if they don't have an equal resistance, the resistor with the least amount of resistance will take more current than the resistor with the highest resistance. Then it gets to this point where it rejoins to give us IT again. So the total current is IT is equal to I1 plus I2 for this particular circuit. The voltage remains the same. This voltage, which is VT, is equal to V1 and it's equal to V2. Okay? Let's continue. The total current in the circuit will increase with each resistor that is added in parallel. So if we add more resistors in parallel in a parallel circuit, we are reducing the equivalent resistance of that parallel network. Okay? So if we are reducing the resistance, and we know that resistance and current are inverses of each other, the current will increase because the battery has to now supply less energy to overcome what? The resistance. Okay, so this is an illustration to demonstrate that. Imagine this first resistor has, let's say, 2 ohms. The second one, okay, let's say we start with this one. All the current, the pink, the blue, and the green will flow through this resistor. Okay, so the resistance is going to be 2 ohms. But if we add another resistor, let's say of 2 ohms as well, in the same circuit, in parallel to the first one, the total resistance is not going to be 4 ohms. It's going to be a fraction of that. Okay, so if the resistance is decreasing, the battery now does less work in driving current through the circuit. So the current is going to increase because now we're using less energy to overcome resistance. If we add a third one, the total resistance will always be less than the lowest resistor, the lowest resistance of the smallest resistor. So if we add a third one, the resistance is going to be even decreased further than what it was when we had only 2 resistors connected in parallel. This only applies to parallel circuits. In a series circuit, if you increase the number of resistors, the resistance increases. In a parallel circuit, if you increase the number of resistors, the parallel resistance decreases. So as the resistance decreases, the voltage does less work in driving the current, and hence more energy is supplied. The current will increase, okay? So if you increase the number of resistors, you decrease the resistance in a parallel circuit. But in a series, if you increase the number of resistors, the overall resistance increases and the current will decrease. In a parallel circuit, as you increase the number of resistors in parallel, the current will also increase. Let's continue. Now let's do a couple of questions. There's two of them. And after these questions, we will take a break and do a demonstration for parallel circuits. The first question is, what do we know about the total current through the battery in a circuit that has resistors connected in parallel? What do we know about the total current through the battery in a circuit that has resistors connected in parallel? Question 2. What do we know about the total voltage across the battery of a circuit with resistors connected in parallel? So first question, what do we know about the total current through the battery in a circuit that has resistors connected in parallel? The second question, what do we know about the voltage across the battery of a circuit that has resistors connected in parallel? You have 2 minutes to work through these questions and your time begins now. When you're done, we are going to discuss the answers together. Welcome back, learners. I hope you were able to answer those two questions. Before we discuss the answers, I would like to remind you that we have a WhatsApp line. If there's anything that you need clarity on, you can send your questions through to 064 748 8913. That's 064 748 8913. Let's quickly discuss the answers to these questions, then we will take a break and do our practical. First question, what do we know about the total current through the battery in a circuit that has resistors connected in parallel? What do you think? Yes, that is correct. The total current through the battery is equal to the sum of the currents flowing through each of the resistors. So each of the resistors split the current amongst themselves. And the total sum of that current is equal to this total current coming from the battery. Question 2, I hope you were able to get that one correct. The second question says, what do we know about the total voltage across the battery of a circuit that has resistors connected in parallel? Anyone? Yes. We know that that voltage remains the same across each of the resistors that are connected in parallel. So it is the same as the voltage across the battery, and it's the same amongst each of those parallel resistors. Okay, so now let's take a break so that we can do our practical demonstration.
Do you know that you are different? Do you know that your fingerprint is different? Is different from your peers, from the people that you are studying with. So do not compare yourself with your peers. Do not compare your results with what they're getting, because you are different. You have your own talents and skills, and also you have your own gifts. Embrace what you can do. Always put in the work to make sure that your results become better than what they were yesterday. But do not compare yourself, because when you compare yourself, you do not know what another person has, and they do not have what you have. So believe in yourself. You are different, and keep on putting the work.
Okay, learners, let's quickly do a practical demonstration to investigate a parallel circuit. Right, so I have a practical activity. So this is an activity which is a practical, right? We do the practical and then we answer questions. So activity 1 says, copy and complete the following table, right? The first column, you have your resistor numbers. You have resistor number 1, R1, resistor number 2, which is R2, and resistor number 3, which is R3. Then you have resistance in ohms, so you need to find the resistance of each of those resistors. Right, so in most cases, especially when you're using like bulbs, you are going to have a rating for your resistance. So it's going to be easy if you're using a light bulb. But when you're using small resistors like the ones here, you will need to calculate it from your results. Okay, but that is not something so hard to do. Right, then we have voltage across resistor V, right? So this records the voltage across the first resistor, the second resistor, and the third resistor. And then we have the ammeter reading after each resistor A. So we are going to take the ammeter reading of the current that flows through each of these resistors. Then we have voltage across battery V, which is the voltage across the battery. So let's just go back to this column here, the ammeter reading after each resistor A. We are going to connect an ammeter in series to all of these resistors to measure the current that flows through each of those resistors. And then ammeter reading at the battery. We are going to connect an ammeter in series to the battery to measure the total current. Okay, so without any waste of time, let us continue. So this is how you're going to set up your circuit. Number 2 says, set up a parallel circuit with 3 resistors in parallel and 3 1.5 volt or a 4.5 volt battery. So you have 3 cells, which gives you 1.5 plus 1.5 plus 1.5, that's 4.5 volts. And then you have 3 resistors that are connected in parallel. Each resistor has its own line of current flowing through it. Like for instance, in this case, we have this. Okay, for now, the circuit is open, there's no current flowing. So this is going to take current to this resistor, and then it's going to split to that resistor, and then it's going to split to that resistor. So there's going to be current flowing in this direction, current flowing in this direction, and then current flowing through that direction. So it splits 3 times, okay? So this is how we are going to connect our circuit. And then in series to each of these resistors, we are going to connect an ammeter to measure the current flowing through each of these resistors. As you can see, each of these ammeters are in series. And then to measure the voltage, remember we said we connect the voltmeter in parallel to each of these resistors. Voltmeters have a very high resistance. So if we were to connect them in series, there will be no current flowing. And then the ammeters are connected in series because they have a negligible resistance. So without any waste of time, let's just get to these practical. Okay. So the first thing that we need to do is we fill in the second column in the table by reading off the resistance of each resistor. This should be written on the resistor. Unfortunately, these resistors don't have a resistance rating, but I have already calculated them using the results from the practical. Okay. Then number 4, use a voltmeter and measure the voltage across each resistor. Make sure you connect the voltmeter for resistor 1, R1. Record the voltmeter readings in the 3rd row. Number 5, measure the voltage across the battery and record the reading in the last column. And then number 6, using the ammeter, take the current readings for each of the resistors. 7, take the ammeter readings across each resistor and record the summation in the table. So without any waste of time, let's just get to the practical. So I've already connected the resistors in parallel, okay? And currently there's no current flowing. That's why no bulb is glowing. So as soon as I connect this, we should see some glow, okay? There, as you can see, this bulb is shining bright, this bulb is shining bright. That one you can barely see that it's on, okay? There is a reason for that, and you will need to answer a question based on that as well. So now we're going to take the voltmeter reading across the battery, okay? So this is my digital voltmeter, and I'm going to connect it in parallel, not in series. Connecting in parallel. And then I'd switch it on to check the voltmeter reading. Okay, it seems we are getting 4.5 volts, okay? So we have 4.5 volts across the battery, okay? Now let's disconnect it from here and go to each of the resistors and take the voltmeter reading. We always connect the voltmeter in parallel to each resistor. So the voltage across the first resistor is still 4.5 volts. Interesting. Let's look at the second one. Okay. This is the second resistor. Let me just reconnect this. The voltage is still 4.5 volts. It's not changing. I wonder why. Then let's take it to the last one. And it's still 4.5 volts. Interesting. I wonder why. Anyway, let's put the voltmeter aside. Now, let's use our ammeter and measure the current. Okay. I'm going to connect this like that. Okay. The current across the battery is 4.89 amps. Okay. Now let's measure current across the first resistor. I'm going to connect this terminal here because it has to be in series. So it's there, and then it's here. Okay. That gives me a current reading of 3.14. Now let's do the second one. There. That's 1.53. And then let's connect the last one, the very last one. Okay, give me a second. There we go. It is giving me 0.22 amps. Okay, right. So I hope you were taking down the recordings of these voltmeter readings and the ammeter readings. So let's quickly turn off our circuit so that we can continue to answer questions based on these results. Okay, so the last step was to take the ammeter readings across each resistor and record the summation in a table. We've already done all of that. So now we are going to answer the questions based on the practical that we just observed or conducted. All right, learners, let's quickly go through our results from the practical. When we measured the voltage across the battery, we found a voltage of 4.5 volts. And when we measured the voltage across the first resistor in that parallel network, we got 4.5 volts as well. And across the second one, it was still 4.5, and the third one. So the voltage was consistently not changing throughout the parallel circuit. It was the same throughout all those components. Then we measured current. The total current that was measured across the battery was 4.89 amps. And the current across the first resistor was 3.14 amps. Across the second resistor, it was 1.53 amps. And across the third one, it was 0.22 amps. Now, to find the total current that is across those resistors, we want it to be equal to the current coming from the battery. So we add 3.14 and 1.53, and 0.22, and see how much it gives us. It gives us 4.89 volts. This is a characteristic of a parallel circuit. Then we needed to also find the resistance, but unfortunately the resistors that we were using were not rated. We didn't have the resistance rating on those resistors, so we had to use a formula. The formula is V equals I times R, V being the voltage, I being the current, and R being the resistance. We already have the voltage is 4.5 for all those resistors, and the current is 3.14. So we need to rearrange this formula so that R is the subject of the formula, and we can just divide what remains, right? So if we rearrange the formula, we get R is equal to V over I. V being this voltage, I being this current. So for the first one, we divide 4.5 by 3.14, and we get what? 1.43 ohms. The second one, we divide 4.5 by 1.53, and we get 2.94 ohms. And lastly, we divide 4.5 by 0.22 amps. We get 20.5 ohms. Okay, so these are the results from the practical, and we are going to use this to do the questions for our activity. Okay. Number 8. Compare the added ammeter readings at each resistor to the total ammeter reading measured at the battery. A. What do you notice? B. What conclusions can you make about the total current flowing through the battery and the sum of the currents at each resistor connected in parallel? 9. What did you notice about the voltage at any point in the circuit? 10. Which resistor had the highest current flowing through it? 11. Which resistor had the lowest current flowing through it? And lastly, what is the relationship between the resistance of a resistor and the current flowing through it when the resistors are connected in parallel? Now, because our practical took quite some time to demonstrate, we will do these questions together. Okay, the first question says, compare the added ammeter readings at each resistor to the total ammeter reading measured at the battery. A. What do you notice? Okay. The added ammeter readings of the ammeter are equal to the current measured at the battery. When we added the ammeter readings for all three resistors, they gave us the total current that was delivered by the battery. I hope you were also able to observe that. Number B. What conclusion can you make about the total current flowing through the battery and the sum of the currents at each resistor connected in parallel? What we can conclude is that the current delivered by the battery is split amongst the resistors connected in parallel, which is a characteristic of a parallel circuit. Let's move on. What did you notice about the voltage at any point in the circuit? Yes, that's correct. The voltage remained constant throughout the circuit. At the battery, first resistor, second resistor, and third resistor. And that is a characteristic of what? A parallel circuit. Number 10, which resistor had the highest current flowing through it? Which resistor was that? Well, the only way to answer this question, because the first two were glowing in equal brightness, but the third one was a bit dim. So you can use the resistance values that were on the table to answer this question. Resistor 1 had the least resistance, and hence it will be the one to glow the brightest. Why? Because we said more current flows through the resistor that has the least amount of resistance, and less current flows through the resistor with the highest resistance. And I think I just gave you an answer for the next question. 11. Which resistor had the lowest current flowing through it? Everyone? Yes, I've already given you the answer. It's resistor 3. Why? Because it was glowing dim, and when we calculated its resistance, it was very high. It was 20.5 ohms. Okay? So it had to be the one with the least amount of current flowing through it. Last question. What is the relationship between the resistance of a resistor and the current flowing through it when the resistors are connected in parallel? We've already done this question plenty of times by now. I'm sure everyone should be able to answer this one. What is the relationship between the resistance of a resistor and the current flowing through it when the resistors are connected in parallel? Yes, that is correct. The greater the resistance, the smaller the current will flow through it. Why? Because resistance is inversely proportional to current. When resistance is high, there's less current. When resistance is low, there's more current. Okay? I hope you understand that, and I hope you enjoyed the practical. Now, let us do 2 more questions and then we can summarize our lesson. A. What happens to the current strength when more resistors are added in parallel in a parallel circuit? B. What do you think will happen to the brightness of a light bulb if another light bulb is added in parallel? Okay. The answer to the first question is, okay, what happens to the current strength when more resistors are added in parallel in a parallel circuit? The current strength will increase. Why? Because the resistance is decreasing. When we add more resistors in parallel, we are decreasing the overall resistance. Okay. B, what do you think will happen to the brightness of a light bulb if another light bulb is added in parallel? Okay. The brightness will increase. Why? Because if we're adding another bulb in parallel to the first one, the overall resistance will decrease and hence the current will increase. Okay. Now, let's summarize our lesson so that we save time for the WhatsApp questions. We said that a parallel circuit provides multiple pathways for current to flow. It provides more than one pathways for current to flow. And we said that the voltage is the same across each resistor connected in parallel. The total current through the battery is equal to the sum of the currents through each of the resistors connected in parallel. The total current in the circuit increases with each resistor that is added in parallel, while the parallel resistance will decrease. So the overall resistance or the equivalent resistance of the circuit decreases when we add more resistors in parallel, but the current strength will increase. The total voltage across the battery is the same as the voltage across each of those resistors that are connected in parallel. And resistors connected in parallel are known as current dividers. That's why we have multiple pathways for current to flow. Resistors in parallel split current and we call them what? Current dividers. So now let's quickly go through your WhatsApp questions. Right. Let's see what is there. Okay. This is not it. Okay. What is the difference between a resistor and a battery? I like this question. It's a very good question. Thank you for your question. A resistor is a conductor that opposes the flow of, charge. It opposes the flow of charge or current. That is a resistor. It's a conductor that makes it difficult for current to flow through. Voltage is the work done to drive current through the circuit. So a resistor causes a disturbance, or it opposes the flow of current, and voltage provides energy. It's the energy supplied by the battery to drive current. So you asked, what is a battery? Oh, a battery is a combination of of 2 or more cells that are connected together in a circuit. Right. So one cell is defined as a system in which certain chemical reactions will cause the flow of electricity or the flow of current through an external circuit. A battery is when you have more of this, right? When you have two or more of these systems that has chemical reactions that can cause the flow of current through an external circuit. So in other words, the battery provides energy for current to flow. The resistor prevents or tries to prevent the current from flowing. Okay, I hope that answers your question. Thank you so much for your question. Let's see if we have any more questions. Right. There's no question here. And okay. Right. So let's go back to our lesson. Okay. In the absence of questions, I would like you to do the following after completing this lesson. At the bottom of your screen, there's going to be a button that says complete and continue. You're going to click there and you will get a message that says congratulations, you have completed your lesson, and you will get bonus points. Right. So that being done, that brings us to the end of our lesson. Thank you so much for joining me for this lesson. It's been a pleasure sharing the information on parallel circuits. I hope you enjoyed the lesson as much as I enjoyed delivering it for you. Now, what I needed to do from here is, okay, this is the end of term 3, and we are going to begin with term 4. So in term 4, we are going to look at things like planet Earth and beyond, layers of the Earth, the lithosphere, and etc. I hope to see you then. Right. For now, what I need you to do is I want you to take care of yourself, wear your mask, sanitize your hands, and keep your distance, and keep safe until we meet again in term 4. It's been a pleasure hosting you for these lessons. My name is Kwanele Dlamini, and this lesson was proudly brought to you by the Gauteng Department of Education. Thank you so much.